So let's get right into it. Back in 2020, some researchers at Google dropped a paper with a title that sounds, I don't know, more like a clever saying than a research paper. But an image is worth 16 by 16 words. Well, it turned out to be the opening shot of a revolution in how we think about AI and how it sees the world. The whole thing really starts with this one simple question. What if an AI could look at a picture not as just a big grid of pixels, but what if it could read it? Like a sentence, piece by piece. This single idea was about to go up against a decade of established thinking in AI. Now, to really get why that was such a wild idea, you have to remember what the AI world looked like back then. For the longest time, AI was basically split into two totally separate kingdoms. You had the world of seeing, and you had the world of reading, and they were ruled by completely different technologies. So on one side, you had computer vision. This was the domain of convolutional neural networks, or CNNs for short. These things were the undisputed champions of anything image-related. And on the other side, you had language. This was where the transformer architecture had just completely taken over, powering all the big models like BERT and GPT. Two different problems, two different tools. And here's the key thing to understand. CNNs were so good with images for a reason. They had these built-in assumptions baked right in, what the experts call inductive biases. Basically, they came with a cheat sheet. They already knew that pixels close to each other probably belong together. That's locality. And they knew that a cat is still a cat, whether it's in the top left or the bottom right of a photo. This gave them a massive head start. And then came this paper from Google. The researchers basically asked, what if we just ignored all of that? What if we didn't need a specialized tool for vision? What if we could just take the king of language, the transformer, and teach it how to see? And the core idea, right here in their own words, is almost shockingly simple. Instead of building some complicated new vision system, they just thought, hey, let's just make the image look like a bunch of words. And here's exactly how they pulled it off. First, you take a normal image and you just slice it up, like a pizza. You chop it into a grid of smaller, equal-sized squares. These little squares, or patches, are the 16 by 16 words from the title. And then, this is the really clever bit, they took that grid of patches and just laid them out in a line, one after the other. All of a sudden, this complex 2D image is now just a flat one-dimensional sequence. It's a format that a transformer, which is used to reading sentences, can handle no problem. Okay, so we've turned a picture into a sentence. But how does a language model actually make sense of it? Let's peek under the hood of this new model, which they call the vision transformer, or VITE, and see how it actually learns to see.
You'd think it would be super complicated, but it's not. The whole process is incredibly simple. First, each little image patch gets converted into a string of numbers, a vector. Second, they add a little tag to each vector that says, hey, this patch came from the top left, or this one was from the middle. And that's it. You just feed that whole sequence into a totally standard off-the-shelf transformer. No special vision tricks at all.
And this is where the magic really happens. With almost no built-in knowledge, the model had to learn what an image even is from scratch. It figured out the whole 2D layout just from those little position tags. And because it's a transformer, right from the very first layer, some parts of the model could look at the entire image at once, getting the global picture. That's something a CNN can only do way at the end of its process. Okay, so the theory is super elegant, but that leads us to the billion-dollar question, right? Could this simple, general-purpose idea really stand up to the highly specialized, fine-tuned CNNs that had ruled computer vision for years? And at first, the answer was, well, a pretty clear no. The researchers themselves said the initial results were seemingly discouraging. When they trained the vision transformer on the standard, medium-sized ImageNet dataset, it just didn't do as well as a similar-sized CNN. Ouch. So, why did it fail at first? Well, it all comes back to that inductive bias idea. Remember the cheat sheet? CNNs have that built-in head start for vision. The vision transformer, on purpose, has almost none of that. It doesn't assume anything. It has to learn every single basic rule of vision from absolute zero. And on a medium-sized dataset, there just wasn't enough information for it to learn all of that from scratch. But, of course, the story doesn't end there. The researchers had a hunch. They thought, maybe the problem isn't the model. Maybe the problem is how we're feeding it. And this is where the story takes a huge twist. This was their big realization. The vision transformer wasn't weak. It was just starving. It didn't need a cheat sheet to get started. It just needed a truly enormous amount of food for thought so it could figure out the rules for itself. It needed a much, much bigger diet. And when I say bigger, I mean way bigger. They fed it the JFT 300M dataset, a massive private dataset from Google with over 300 million images. To put that in perspective, that's hundreds of times larger than the standard dataset they started with. And this chart just shows you the incredible result. Look, when trained on the smaller dataset, the VIT is lagging behind the CNN. But when it's pre-trained on that massive JFT dataset, holy cow, it doesn't just catch up, it completely blows past the state-of-the-art CNNs. And here's the proof in the numbers. Their biggest model beat the best CNNs on several key tests. But here's the kicker, it did all of this while using significantly less computer power to train. So it wasn't just better, it was also more efficient. That's a huge win. So this wasn't just about setting a new high score on a benchmark. This was the beginning of a whole new way of thinking in AI. It changed how people approached not just vision, but maybe everything. So what's the big takeaway here? Why does this all matter? Well, a few things. First, it proved that one general type of model, the transformer, could be a rock star at completely different things. Second, it showed that if you have enough data, raw scale can actually beat clever, specialized designs. And finally, it started to tear down the walls between different fields of AI, like vision and language. If there is one single thing to remember from all of this, let it be this sentence right here. This whole experiment proved a new law of AI, if you will, that large-scale training trumps inductive bias. Having the ability to learn from massive amounts of data is more important than having a built-in head start. And that really leaves us with a fascinating question for the future. This paper broke down the wall between how an AI sees and how it reads. It suggests that maybe, with the right model and enough data, all kinds of intelligence problems are really just sequencing problems underneath. So you have to wonder, what other walls are about to come tumbling down?